This tutorial is going to focus on some basic biochemical redox chemistry. And so what we're going to do here is take a step back and review a couple things again that you learned in Gen Chem. So oxidation is associated with the loss of electrons. This is often accompanied by loss of two hydrogen atoms. So we're losing electrons and protons at the same time here. This is often accompanied by a gain of oxygens. The reverse of that is reduction, which is a gain of electrons, often accompanied by a gain of two hydrogen atoms, again in the form of electrons and protons. And this is often accompanied by a loss of oxygen atoms. So we've talked about being able to calculate oxidation states, oxidation numbers. Fortunately for us, in the kinds of biomolecules that we talk about, we have to deal with only a few atom types in most cases. Of course, there are always exceptions. So we know that hydrogens are almost always in a +2 oxidation state. Oxygen and sulfur are almost always in a -2. Halogens -1, and nitrogen is typically in a -3. It's the carbon oxidation states that are going to vary more than anything. And we've talked about this before. There is another tutorial about calculating formal charges and oxidation numbers. So I'm not going to go through that in a lot of detail right here. Just go back and look at that tutorial. If you have questions, bring them to discussions. So again, here's a kind of a layout of common organic functional groups, and the important thing here is to understand that starting at the top here we have the most reduced form, and going down we have the more oxidized forms, and in between we've got intermediate steps. And what you should do here is go through and calculate the oxidation numbers for the carbons in these important functional groups. For example, this carbon versus this carbon versus this carbon, this aldehyde carbon, this carbon if it's bonded to an alcohol, a sulfhydryl, an amine, etc. These kinds of things. Okay, so we've already talked about the idea that enzymes as catalysts have a lot of restrictions, and we have the same kinds of restrictions for these biochemical oxidation reduction reactions. So we're dealing with relatively constant oxygen partial pressures, which are relatively low, negligible hydrogen partial pressures. So to do a reduction, we can't just do what we do in the lab, which is add a catalyst, throw several atmospheres of pressure of hydrogen into a vial, cap it up, and keep it until we get what we want. We're dealing with a constant temperature, almost always an aqueous solution. And if we just throw in strong oxidizing or reducing agents, right, things like permanganate for an oxidizing agent, or platinum on carbon and hydrogen gas as a reducing agent, or sodium borohydride, something like that, we'd get too many undesirable reactions, right? We'd just oxidize or reduce anything in the area that's present, and that's certainly not what we want to have happen in a tightly controlled biological system like a cell. So one solution to this dilemma is to mediate intermolecular redox reactions. So if we start off with this compound that has a ketone and an aldehyde functional group here, if we react with glutathione, again we've talked about what glutathione is. It's a tripeptide. It's an antioxidant peptide. It's got a glutamic acid that is linked through an amide linkage through its side chain, carboxylic acid, to a cysteine that's linked to a glycine. So you can get attack on this electrophilic center here, form this intermediate, and then you have an enzyme that'll convert this into this final product. So if you go through and calculate the oxidation states of this carbon here and this carbon here, obviously this guy is going to get reduced, this guy gets oxidized. So you have a redox reaction that's going on within that molecule. Okay, but we need kind of a broader solution here. So what we have are these nicotinamide containing oxidizing and reducing agents, NAD plus or NADP plus, NADH or NADPH. Okay, so the components here are, we have two ribose units, we have a pyrophosphate group, so two phosphates linked together in a phosphodiester linkage connecting both the 5' alcohols, the riboses. We've got 1,3-imidopyridine, we've got one adenine. Okay, so when you link these all together, you have NAD plus, or its reduced form NADH, or if you include a 2' monophosphate on one of these units, then you have NADP plus and in its reduced form NADPH. Okay, I give you a task here to build these. If you're brave, you'll go through and figure out how to put the pieces together, but I've also done it here. So again, the only difference between NAD plus and NADP plus here is the identity of this R group at the 2' position off the adenosine ring here. So if you've got just a hydrogen there, then it's NAD plus. Sorry, it's very easy to get your tongue tied here when you're talking about NAD plus, NADPH, NAD H, etc. Right? So it's you gotta slow down and be very precise. So this is the NAD plus form. If you've got a phosphate here, it's NADP plus. Okay, so if you add, if you reduce this, then you get to this form, which is NADH or NADPH. Okay, now what we have here are two very carefully balanced oxidized and reduced forms. So neither of these are particularly strong oxidizing or reducing agents. If one was very strong and the other was very weak in either direction, then it wouldn't be a reversible system. So what we have here is we want to be able to easily interconvert between these. And we want them to be mild oxidizing and reducing agents for the reasons that we talked about before. So this is actually an aromatic compound, but it's got a fixed positive charge, so it's not as happy as a normal aromatic compound. And this one is not aromatic at all because it's got an sp3 hybridized carbon in the middle. So these guys are kind of flawed heroes in our story here, but they work for what they're supposed to be. We want mild oxidizing and reducing agents. So this pair works very nicely. Again, I stole my own thunder a little bit there. So NAD plus or NADP plus is always an oxidizing agent. It helps oxidize substrates. It itself gets reduced to the corresponding NADH or NADPH. Okay, and NAD plus is commonly used by catabolic enzymes. So these are enzymes that are degrading a molecule. Okay, and NADPH is a reducing agent. It helps to reduce substrates and itself gets oxidized. So NADH or NADPH are both reducing agents, and they get oxidized back to their NAD plus or NADP plus forms. And NADPH is commonly used for anabolic enzymes. These are enzymes that are building biomolecules. So as I said, catabolic pathways use NAD plus, and the cellular balance here is that we have more NAD plus than NADH. So the ratio here is about 1,000 to 1. So we have lots more of this. And anabolic enzymes use NADPH, and the cellular balance here is that we have more NAD pH than NADP+. Okay, so larger number here, right? So about 100 times more of the reduced form here than the oxidized form, whereas the NAD+, we have 1,000 times more than here. Okay? So if we need to do an oxidation reaction, we're going to use NAD+ more often. If we're going to do a reduction, then we're going to use NADPH more commonly. That's the point of this. So here's an example reaction here. So if we have a reduced substrate reacting with the oxidized form of NAD plus here, then we're going to get the reduced form of the cofactor, and we're going to get the oxidized form of the substrate. So we go from reduced to oxidized here, go from oxidized to reduced here. And a specific example here is this reaction of malate going to oxaloacetate, and it's mediated by this enzyme malate dehydrogenase. So again, we're taking this compound. You see the pointing at the major player here. This carbon atom is getting converted from an alcohol to a ketone. So we're going from reduced form to oxidized form. So we need to use the oxidized form of the cofactor, NAD+, and forming the reduced form of the cofactor, NADH. And we also have a proton here. Okay? So the flip side of that is if we were taking an oxidized substrate and making it reduced, or reducing it, then we need NADPH and a proton. We convert that. It's acting as a reducing agent to be oxidized itself. Okay? So when this gets oxidized, it's mediating a reduction. When this gets reduced, it's mediating an oxidation. Okay, so two more examples here. Here we've got an alcohol being converted to an aldehyde. If this R group is a hydrogen, if it's a carbon, then we've got an alcohol going to a ketone. But in the enzyme, you're going to bind the cofactor, and we're just showing the business end here. So this is the nicotinamide portion of the cofactor. And because this is the oxidized form, it's most likely going to be NAD+. So we've got a general base in the enzyme active site that's going to grab this proton. These electrons come down to form the double bond, and this hydride is going to shift to the NAD+. So this is going to form our NADH, and this is our proton that we talked about in that reaction. Okay, so you go reduced substrate, oxidized cofactor, reduced cofactor plus that extra proton. The opposite of this is if we take the oxidized form of that substrate and we convert it back to the reduced form, right? Either aldehyde or ketone going to alcohol here. Now we're going to push electrons back through this pi system. We're going to get a hydride shift to our substrate. We're going to pick up this proton back, and we're going to, so in this case we need a general acid catalyst here. And again, because we're talking about the reduced form of the cofactor, it's more likely to be NADPH, and reduced substrate, or sorry, oxidized substrate becomes reduced cofactor becomes oxidized, and we're including this proton that's being converted. So we need to take that into account when we're writing our balanced chemical equation. Okay, we'll see some more examples of these in the problem set, kind of give you a little bit of practice.